Okay. Okay, I'm gonna turn back as well so I can see the paper. Okay, so I actually wanted to introduce the problem first because it's a very interesting problem that, again, is very different than the ones that we, or at least I've faced in machine learning. And here, the problem is the following: you have a lot of situations in computer graphics when you want to have like really high fidelity images or rendered scenes. But in order to do that, you either need to store very large amounts of information and then query it, or you have to find some other way of compressing that information and then also still being able to query it very quickly. And so, for example, I think a good one is, if you can see my screen, that they have like the 4 different tasks that they tested this method on. And the gigapixel image is an image that has more than 1 billion pixels in it. And so, for example, ideally, you'd want to be able to store an image of that size, but without having to store 1 billion pixels. And so this is a method for using essentially less parameters to store that image and then query it. And the other element of this, besides being able to come up with like a compact representation of an image or other elements of a scene that are required for rendering, is that it can be trained quickly, because you and a lot of the main applications of graphics right now are in video games, and you want to be able to, for example, generate a scene and then cache elements of the scene, like, for example, the neural radians field, or for an object, the signed distance function. So a signed distance function would tell you like the position of an object, but like in a very fine level of detail, because you could query where the surface is within your scene. And then the neural radians field would tell you how light is propagated through the scene. And especially the second one is actually really computationally intensive to calculate. So it's not something that you can do very easily real time. It's only now that we're starting to see more accurate light scenes. And that's one, because of computation, increases in computation, and 2, because of techniques like this. Although I doubt that it would be cool if these were in video games and movies already, but I don't think they are. So there's the 2 elements to this. One is taking an image or some other visual information and creating a compact representation that requires fewer parameters than just saving the whole thing, and then being able to train it really quickly and being able to query it really quickly. So 3 things, sorry. I hope that describes what the goals of this paper are, or what it, and just as an additional piece of background, so the way these things would be used is you have like all these, what they call neural graphic primitives, or just we'll call them graphic primitives. And then the idea is you can query them real time in order to figure out certain information about a scene. So instead of having to generate the scene from scratch, you'll have like, okay, I need to load this mechanical cow thing here into my scene. So I'll just load the function for it that I've learned, and then I'll put it into the scene that way, instead of having to like pixel by pixel generate, or in these cases, because they're 3D scenes that are then projected into 2D, generate it. Cool.
Doesn't it also then combine these together to form new images?
Yeah, I think that's the idea. Or, for example, let me go down. I like how many images there are in this paper. They do a really good idea. Good job. So see this scene over here in the middle image where my cursor is. So say you're in a video game and you walk into the scene. When they're generating this scene, they're actually generating like the 3D model of the scene and all of the light propagation through it. And it doesn't matter what your viewpoint is, the light will still propagate through the scene the same way. So the idea is that then you could change your viewpoint and still query that in order to maintain like the same level of fidelity, and then you don't have to, each time you move, do ray tracing in order to figure out where the light is. Okay, so is there anything? Okay, and so no graphics. Where should I start at the introduction or should I start here? I'll start at the introduction. One thing that I wanted to talk about, which is like an underlying something they use in this paper to cause some of the speed up, which is obvious, is they use fully fused Cuda kernels, which are actually not a contribution in a scientific sense, but a contribution in an implementation sense. And it seems like the main author of this, Thomas Mueller, he actually wrote the fully fused Cuda kernels. And essentially what they are is that so in a GPU, each kernel performs a different operation. So for example, you might have an add kernel and a multiplication kernel. And the way that they work is that each kernel will read a number, perform the operation, and write the result. And then that means that for performing two operations with two separate kernels, you have to do two reads and two writes. But if you want to perform those in succession, and you don't really need to store the intermediate value, then you can fuse those kernels and reduce the number of reads and writes of values. And so they're using in all of their experiments these fully fused CUDA kernels, and they say that creates like a 10x increase in their method, which is not necessarily part of their method, but one of the reasons why it's there. So I just looked that up when I was like, what's a fully fused kernel, if anyone's interested. Okay, so let's go to the introduction. Again, here, I actually like the way things are written in the introduction. So it says computer graphic primitives are fundamentally represented by mathematical functions that parameterize appearance. And then they say the quality and performance characteristics of the mathematical representations are crucial for visual fidelity. So they want the image to look good. We desire representations that remain fast and compact while capturing high frequency local detail. So that's a lot of what they're trying to do here. And you can see that because they zoom into like these really really large images just to show like this is how good the detail is. I have a feeling the authors have like an amazing eye for detail based on the images they show. I have a really good example later on of this because they point out an issue with their method that you can't see unless you zoom in really close to the image. Yeah. And so like one way you could, one initial or like the most obvious method for doing this of creating a mathematical function to parameterize a scene or some visual information is that you give like the location of some element of the scene, like the pixel location, and then you have a mapping which tells you what the color is. And one thing that they say is like in the state of the art approaches, the important commonality of these approaches is an encoding that maps neural network inputs to a higher dimensional space. So for example, in these cases, you get like the pixel location and it maps to a much larger vector, which in this case, you learn in order to like basically store information and then you propagate, you put that through a neural network. And there's a couple of reasons why that's useful, but the main one is that it's much faster. So instead of
Yeah, I was stumbling over this because high dimensional really implies bigger, right? So why would you spend more space rather than smaller space if you lower the dimension? Or is it some other part of the representation shrunk?
So the way I think of it is like the most memory consumption that you could take from this operation is if you had a lookup table, right? You get the position and it outputs your answer.
Yeah.
And they're trying to find a way to reduce the size of the lookup table. So when they say a higher dimensional representation, what they're saying is that like they give it the coordinates and they'll get like a much higher, larger vector, but that's really just like a smaller lookup table.
The index of the table is essentially higher dimension rather than what is being stored.
Yeah. So in this case, well, we'll go through the method, but you could think of it, for example, this case, the higher dimension, the input is a position encoding. I mean, a position of some kind, and the output is like a vector of a higher dimensionality, which in theory stores information about like what's at that point, which you can then you use the neural network to figure out like the value of interest. So for example, it could be like, in this case, I think you go from like two numbers, which is your position, to a vector of size like 19 times 2, 38. And then you go back down to like 5 or something when you put it through the MLP. So but I agree, I had to read that twice over 2 days to understand what they were saying, because I think that they're trying to introduce their method, but they can't think of a great intuitive sentence to explain it. Okay, they say so the idea is you have some kind of lookup table that you use, and then you propagate it through a network, and that makes the network much smaller, which speeds up the whole query of using that method. Most successful among these encodings are trainable task-specific data structures that take on a large portion of the learning task. So basically, the state of the art in these fields at this point is their data structure is similar to the one that we're using, which is that they're proposing, which is a hash table, but they're task specific, which means that you can't easily translate them from, for example, memorizing a gigapixel image to using assigned distance to learning assigned distance function to. So one of their arguments is that their method is more general, and then also their method has a much simpler training process. In essence, there's a lot of details which are in the previous papers, like, for example, there's other papers that use hash tables, but they have to do things like manage control flow, which I've looked up a little bit, but didn't really look into. Or they have to like modify the structure of the hash table during training, which is another complication, whereas here it's just you choose two numbers, you get your hash table, and it works. And yeah, that's what they say over here. We address these concerns with our multi-resolution hash encoding, which is adaptive and efficient, independent of the task. It is configured by two values, the number of parameters t, and the desired finest resolution and max. Although I disagree, I think it's configured by 3 parameters, because you also have to choose the dimensionality of the encoding. So for them, they use a dimensionality of 2. Yeah, here they talk about some of so their two main what's it called? Advantages are, I just want to make sure I'm not missing any questions. Okay, good. The two main advantages are adaptivity, so it's more general, and then also efficiency, like the lookup of a hash table is very efficient. And specifically the one they're doing can be parallelized between the different levels of resolution. Okay. Let's go into background, and I'll try to go through this really quickly, and we can go back to it. So they introduce the idea of encodings. This first part of the background, where it says early examples of encoding the inputs of a machine learning model into higher dimensional space, include the one-hot encoding and the kernel trick, by which complex arrangements of data can be made linearly separable. I feel like encodings are used ubiquitously throughout machine learning, so I don't know. I think maybe they should have just stuck to maybe position encodings, which is kind of what they're talking about for the rest of this. And they introduce the position encoding that's used in the transformer architecture, which they call frequency encodings. And it's actually really interesting if you read up on it. And I have a reference that I wanted to put in the chat so people could see if they're interested in reading up on it more. Because when I read up on it, I was really impressed by like the sophistication and thought that went into this part of the transformer, which where is it? Oh, there it is. Okay. No. Is this 1 or 2? this was one, and then part two. So anyway, so there are position encodings in transformers. It's like a part of the architecture that's mentioned, but not really explained that much, even in the paper. But supposedly they have an impact on performance. I don't know how big of an impact they have, and you never see it in the code really. But what's interesting about it is they use these sine and cosine functions to calculate the position encoding. And that's one of the reasons why they do this, is because you have variable sized encodings. I mean, sequences in transformers. So you need something that can deal with that variable size. And there's a lot of other good reasons why they use this. But anyway, so one of the things that they say is that one of the first encodings that were used in neural graphic primitives were these frequency encodings. I'm not sure, but I think they were used in NERF. I think they say that somewhere. Yeah. Okay, and then after that, they started using what they call parametric encodings. Parametric encodings, I think, is maybe the wrong word, but basically what they mean is that they're learned encodings. And there's a ton of different ones that are used. And the main idea is that you can really reduce the size of the MLP that's on top of them and make them a lot quicker to query and train. And it says that by reducing the size of such parametric can typically be trained to convergence much faster without sacrificing approximation quality. Okay. Then they talk about sparse parametry encodings. That's kind of what they're talking about here. Again, I don't know if it's the correct term, but really what they're trying to say is that, like, dense parametric encodings, for example, if you're just trying to learn an encoding for each part of the grid you're learning, you'll end up learning like having to learn parameters for essentially empty space or fixed space, like basically parts of the image that don't have a lot of detail. You'll have parameters for them where you won't have, where you don't need it. And that's actually one of the main ideas or contributions of this method, is like using these hash tables in order to learn where you need to learn the detail, or like to learn where the detail should be learned for. I don't know exactly how to say that, but we'll go back into that when we talk about the method. But instead of using a dense representation, you use a sparse representation, and then you kind of leave it up to the model to learn where it should learn fine resolution detail, as opposed to forcing it to learn it everywhere. Yeah, that's what they're saying. And then should we go through this? Yeah, maybe. And then they talk about the different methods in their related work through this figure. Let me zoom in a bit, because you actually need to zoom in to see a lot of the differences that they talk about. So here's a MLP that's just trained without encodings. And you can see training time and peak signal to noise ratio. But essentially what it learns is like a very smooth representation of the image that doesn't have a lot of detail. Here you can see the frequency encodings that are being learned and what they look like. And then you have the dense grid, which is the first learned representation. I don't know. I feel like it's subjective which of these two are better. And then you have the dense grid with multiple resolutions, with the point being that you can learn, if you look at the dense grid without multi-resolution, it's using 33.6 million parameters, and with it, it's using 16.3. So essentially, it's saying you can get the same quality with less parameters. Okay, cool. And then you get to theirs, which uses even less parameters based on your choice of T, and it gets like very nice fine-grained detail. So yeah, that's a little bit of a summary in terms of images of the different methods. And they talk about hash collisions, but I'd rather talk about that when we introduce the method. Okay, so here's the method in a picture, and I think that's the best way to describe it. In general, I think they have great graphics in this paper. So let's pretend they're using a multi-resolution hash table, but let's just say that it only has one resolution, and it's the blue one here. So you floor and ceiling the position in an image or in a scene that you want to figure out the property for, and you get like 4 corners, which are in this case, in the blue one, 0, 4, 1, 7. You take that position information and you feed it through a hash function, and it's going to give you an index in that hash table, which is in this case 0 to 7, so they only have 7. One key element of this, which I think is important to notice, is that they're using a hash function, which means that probably you'll see points that are near each other having the same index. So for example, 0 and 4 might be in the same row in the hash table, but not always. And then also you have the issue that with a hash table, you could take 2 opposite sides of the image and map them to the same row. And that's what's considered a hash collision, because the whole idea of a hash function is that it's a pseudo-random mapping. And if you're thinking about it in terms of learning, what that means is that you're going to have a hash table which you're trying to learn a representation for that's supposed to encode information like detail about the image. And it might be having to learn information about an image like at the top right corner and in the center. And in the center, it's much more important to know the detail, because usually like the center of an image has the subject of the image, and on the side it's just background that's maybe like low frequency information or doesn't have a lot of information. But you have to make that trade-off in terms of learning. So anyway, you map you get your 4 corners, you figure out your encoding for those 4 corners, and then you use linear interpolation to figure out your encoding for the specific point, and then you take that and you concatenate it onto your feature vector, where and so you do that for each resolution. So maybe your first resolution is just 4 quadrants, and then your second resolution is 16 quadrants and so on of the image.
The hash table stays the same, right? Throughout the size of the hash table.
Yeah.
But that was also something.
So the hash table stays the same, and what that means is that at small amounts of, when you have for the lower resolutions, you have usually a 1-to-1 mapping. So there's no need for the hash function, and you could actually just like take each index and map it to a row in the table. And then for the higher dimensional ones, there is hash collisions, which means that multiple different areas are mapped to the same row.
And F is
F is the dimensionality of the encoding.
Yes, that is where this higher dimensional.
Well, the higher dimensionality, I think, is also because you're concatenating multiple resolutions on. Because 2, I was like, wow, 2 is really small. Anyway, so you get all your hash encodings, and that's L, which is the number of different resolutions you have hash tables for, times F, which is your encoding size, and then you have some auxiliary features. Like in one of the experiments, they also fed in the materials that they were trying to figure out, I think like the radiance or like the reflection for, or something along those lines. Then you feed it through a neural network and it gives you whatever answer you're looking for. Yeah.
There's a question.
Oh, okay.
Will you use an open encoding instead of the partial table?
You could, but the whole idea here is that the larger the model is, where you have to perform like matrix, like different functional operations on it, the slower it's going to be. So you actually, and also the longer it's going to take to train. So that's why these tables are important, because they're very quick to train and they're very quick to query.
You said at any point of calculation by any point, you only have like a very small number of parameters get touched from beginning to end.
Yeah. That's actually one of the points that they make. Where do they make it? Maybe they make it farther up. But the point is that, so for any point that you're trying to query when you're training or doing inference, you only have to touch 4 rows in the hash table. And then the parameters of the neural network. So even though you might have like 16 million parameters in the hash table, you end up updating a lot less of them. Or I think actually if you're training over in the entire image, you end up having to calculate gradients for a lot less gradients, because you don't have to calculate like the gradient of each row with respect to every pixel in the image, whereas you have to do that for the neural network.
See the linear interpolation between the 4 points. Is that, but here in the picture, it looks like the representation is shifted. So is it like an equal mean of the encodings that we have here? Like this is what for red. Red has 4 hash points, and are they just rather into the picture?
Yeah.
Here they take the interpolation. Is it because the hash points wouldn't necessarily form an actual square in this encoding space? I think it probably form some kind of parallel because you don't have to be orthogonal to each other.
Well, they use a grid. So the resolution determines a grid on the image. And so the 4 points are just like the points on the grid on the image.
Sure, but the red points, are they the F encoding? Right? So F is,
Yeah.
These are only squares or particular squares because we choose F to be 2, right?
Yeah.
If F was 3, then the right hand there would be some kind of.
Well, they're doing linear interpolation based on the distance of the point from the grid corners. So the weight is based on the grid corners.
Of the original image.
Yeah.
Yeah, because it looks like the. I don't know, never mind. I got confused because it's overlaying the same point. Yeah, it is off center to the right.
Yeah. They use this spatial hash function as their hash function for determining the index of each encoding of each position. And is there any other important information?
So they would sort of iterate over all the pixels in the original picture, and each one gets encoded.
Yeah. Choosing the hash table size provides it yet. So like they said, essentially the hash table, there's 2 parameters which determine it, L and T. And they're saying over here, choosing the hash table T provides a trade-off between performance, memory, and quality. So the lower T is, so the lower the what is it, the depth? No, it's the where's T? Okay, no, it is the depth, I think. Anyway, T is, oh, max entries per level.
The level 7 in the picture, I think.
Ah, T is the size of the hash table, that's it. So the larger the hash table, basically the finer the grain detail that's easily stored. Okay. And they have an image which shows you the trade-off. It's okay here. So here you can see the trade-off between having a T of 2 to the 12 versus 2 to the 17 versus 2 to the 22. And you actually have to zoom in for this to see the difference. So you can see that, like, this is the reconstructed image. And then this is the difference between the different depths. And it's so impressive to me how, like, they actually can replicate this, like these really small lines with this method in terms of replication. But anyway.
Basically, larger means bigger heart shape.
Yeah.
So you can install more diverse right? Because
You have less hash collisions, so you can store exact information in those points.
I mean, it's more than a collision, so you can't say.
Yeah.
Is it just the hash collisions or also the? Yeah, it's the aliasing, like, so essentially you are able to zoom in at the. What? So still the highest resolution they have is only 3.5% of the original image type. It is very bad.
Mhm.
What I was wondering is that so that they mentioned how the training time their methods gets reduced because of this hash. I wonder whether the actual picture loading time will increase that because you have to do a lot of lookups rather than having a method that maybe reconstructs the picture in single steps. So
I'll do all the same question.
Yeah.
If you have a long-term hash title, then computing the hash is slower. You'll probably also be.
Wait, no. Hash computing lookup will be is constant time, right? Because you don't have to search.
How many elements you have. If you consider the size base, then it's constant time, but if there is a large size is bigger hash will be slower.
yeah, also more, right? So if you have if you increase L, then also you do more.
What's interesting is in the experiments, they don't, I'm sorry. They don't talk about inference, like how long the query takes, but they do a lot of real-time usage in their experiments, and they tell you what the total time for it is. So maybe we'll get some answers there. Okay, and I know I've said this a couple of times, but so they have this thing called implicit hash collision resolution. And like, where does it say? I'll just read it out. And it may appear counterintuitive that this encoding is able to reconstruct scenes faithfully in the presence of hash collisions. Key to a success is that the different resolution levels have different strengths that complement each other. Oh no, that's not where's the important part? Okay, when training samples collide in this way, so when basically you have two different parts of the image which are querying the same encoding, and you have to basically the model has to choose between saving information about the one part of the image versus the other. The gradients and the argument is the magnitude of the gradients will determine which part of the which pixel essentially will be given more, will the information be stored for, because the loss function implicitly like weights different parts of the image differently in terms of their importance for whatever objective it's trying to maximize. So their point here is that you don't have to do anything and it deals with hash collisions.
It would be unlikely also that you have more than one hash position across your L different tables, right?
Well, the hash collision is within a table.
Yeah, but you would have to have on several tables at all, whether each one has a slightly different way how they calculate the hash, right? Because of the spatial encoding, because the L factor is according to the calculation. So you could feel intuitive that if you have L1 and then you have to do 1, if you still have L-1 where you don't.
That's true.
That might compensate for that.
I didn't even think of that. Yeah. So yeah, that's the part of their method, but they do identify an issue created by it, which is an issue for them and less for me, but I'm not a graphics person.
Can I ask a dumb question maybe? So the gradients referred to there are the gradients in the loss function, not the gradients in the image itself. Right?
One interesting thing they point out, which maybe has to do with using this real time, is that they say that if you change the distribution of the data over time, and the example they give is, say you want to zoom in on a part of the image and learn really well for that part of the image, the training method itself will automatically do that. So it's online adaptive, that it can adapt to changes in distribution over time. But yeah. And then, yeah, they use linear interpolation essentially. One of the key points is that if they didn't use linear interpolation to choose to calculate the encoding for a position, then you couldn't back propagate as easily through the to the encodings to learn them. So linear interpolation is an important component of the method because it allows you to easily calculate the gradient for each encoding that you're learning. Okay. So now we can talk about implementation. Really, it's a really simple method. It's like a hash table with learnable parameters.
And these parameters also make up your picture size, right? And they say the 3.something%, it's the hash table plus what the output of the neural network.
What the hash table is and the neural network are the model.
Yeah. But say from picture to picture, that would be the hash table would be different.
Yeah.
But then if you have to count the size of the hash table towards your space budget, right?
Yeah. So the hash table, I view the space budget as the hash table and the model. I mean, the MLP, that's like, if is that smaller than an image, than the image itself, and how much smaller is it? They talk a lot about a lot of different implementation details. I think some of the important ones are the ones that I've found is like, wow. They say we use an MLP with 2 hidden layers that has a width of 64 neurons and ReLU activation functions. So essentially they have like 4 linear mappings with ReLU functions. It's a really small network. I found that to be really interesting. They talk about how big the hash tables are, and they say, for example, for the gigapixel image, they use half of the gigapixel image width as their resolution. So I was thinking that means that the hash table maybe is like 3/4 or something, or like 0.6 times the amount of memory as the image itself. So it's still, they're using it's still taking up quite a bit of, like it has quite a few parameters. These, yeah, this whole time I was wondering, why don't they compare it to just like querying the original image? Like there has to be some kind of like showing the benefit of using these methods versus just like the traditional way. But maybe I think there is something here I'm not understanding. Okay, so let's get into the experiments because there's a lot of cool different pictures. So the first one is gigapixel image approximation. So can you store a representation of 1 billion pixels in a smaller representation? And they compare their method to Acorn, which is like a method that is state of the art for this task. And they say that it takes 36.9 hours to train versus theirs, which takes 2.5 minutes. And they say, first off, 10x of that stems from using their fully fused Cuda kernels, but the other 10 to 100x comes from using a much smaller MLP, having to train a much smaller MLP. And if you look at the difference, oh, is this it? No, this isn't it. Where is it? Oh, okay. Yeah, never mind. They're just showing training times here. I don't think they show Acorn. I wish they did. Yeah. The gradients mentioned here are the gradients in the loss function, not in the image. Yes. So the gradients are with respect to the parameters of the MLP and the hash function. I mean the hash table, sorry, not hash function. Hash encodings. So for gigapixel images, they just say that they can approximate them with a lot less training time. Maybe the query speed is just the same. I don't know. And then they say it's faster, and also it has a much less complicated training method. So check better for gigapixel image approximation. For signed distance functions, for anyone who doesn't know what signed distance functions are, it's you give a position in 3D space or 2D space, or I guess you could even do 4D space or any D space. And then it's going to output either a -1, a 0, or a 1. -1 means that the point is outside of the object. 0 means that the point is on the surface of the object. And then 1 means within the object. And I think these functions are really useful for 3D modeling and are used a lot in 3D modeling. But for a really large object, you could see why just like this type of method would be a lot quicker than having to query the actual 3D model. And they compare their method to this method called Encoding. Where's figure 7? Over here. And they say that their method actually performs worse than Encoding, but not that much worse. So you can see here number of parameters, if you can see my cursor. Okay. Number of parameters, training time, and then this metric, which I think is intersection or union, which is just like how good the sign distance function is. And you can see that their method, I guess, is actually here is slightly better, but they say that the Encoding is generally better. Yeah. And so their method basically their method isn't as good as Encoding, but it takes a little bit less time to train and it's almost as good. And yeah, wait. The crazy thing is this is where they identify like the issue with hash collisions, because the main idea is this Encoding is like theirs, except doesn't have hash collisions in the table, is this graininess. This graininess is what they identify as like one of the failures of their method versus that. And you can't even
these designs, right? And I think that is there's areas in
yeah.
sometimes in the low resolution.
That brings you on its
But see, it's like the surface roughness. They say the surface roughness shouldn't be there. But I thought that was crazy because when they said it, I was like, I can't even see it. Do you see how far you have to zoom in to see it?
Where is it on the original picture?
It's not on the original picture. Oh, they don't show the original picture, but
On the right there.
Oh. But they don't show that like that level of detail on the original picture.
Not somewhere on the right picture. Oh, yeah, it's the upper right corner.
But they're saying like this is a failure of our method because it's grainy. Yeah. And you can't. Yeah. So for sign distance functions, they say we're better, but I mean we're worse, but still pretty good. And one point they do make is that the Encoding method is only able to learn the mapping for like a very specific area around the object. See, it says that the sign distance function is defined everywhere within the training volume, as opposed to Encoding, which is only defined within the octree close to the surface. I don't know if that's important. Maybe if you're not close to the surface, then it's really easy. Like you don't need a function for it or something along those lines. I don't know. Okay. And then neural radiance caching. So this is what we talked about before, where they're talking about you want to basically learn the light field of maybe not the light field, but how light falls on objects within a scene, and you want to remember it so you can, when you change your viewpoint, you can query it again, so you don't have to keep calculating it. Because the way that the best way to do that right now is you have your light sources and you'll project rays off of them, and then they'll hit something, and then they'll hit something else, and they'll hit something. But if you think about how these rays propagate, you could have like thousands of collisions for a single ray, and then in reality we have like an infinite number of rays coming out of a light source, but you can only query so many of them within time. So that's why it's so expensive, and that's why they want to cache this. And again, they show the performance of their method, which is the multi-resolution hash encoding versus these triangle wave encodings. And you can see that you get like very much clearer shadows, for example, in the image than you would if you were using the triangle wave. again, I think these images are such a good example of how detailed this author is, because this is the image itself. I didn't even notice this. Like, I didn't think I would notice that if I were looking at it, but I think if you really care, you would. Yeah. And then they do the same thing with neural radiance and density fields. Again, oh, and so one point with these neural radiance caching is that they're actually able to do it real time, and they're able to do it real time at 133 frames per second with this resolution, which is slower than the other method, but it's better in terms of quality. So I guess what the whole point is that these methods might allow us to do ray tracing real time, so we can do ray tracing in video games, which means that we'll get really good graphics in video games in the future, which would be cool if this paper is the one that we're reading and it ends up being in like most video games in the next couple of years.
So those mean that so 60 frames per second, that they do 60 images, which they do for each pixel the hash lookup. Because that would mean if you have a billion, I don't know, what is the image size? Because we have a billion pixels, we have a billion times.
Oh, the pixels, this is the so it's 10 million, or no, it's no, it's like what is that? 2 million pixels.
So it would still be 2 million times, I don't know what that is. 2 billion.
2 to the 19.
Hash lookups times 60, which is quite a lot.
Yeah. One point that they make though is that to make this work, they have to the hash tables have to be smaller than the cache of the GPU.
Yeah.
And if that happens, then you get the speed up, and if it's larger, then you get a significant decrease of performance. So that's like a limiting requirement of the method, that they have to be, the hash tables have to be smaller than the cache. And the way that it works is that they cache for each resolution separately in sequence. So actually they're doing like, it's 2 million times whatever the depth is, lookups. And then they can do it. The no radiance cache is trained online during rendering from a path tracer that runs in the background, which means that the 0.7 milliseconds overhead includes both training and runtime costs of our encoding. Yeah. And so they do the same thing with neural radiance and density fields. Yeah, they compare it again to like a state-of-the-art method. But let's look at the image. Where's figure 12? Oh, this is it. So yeah, here's another example. So the point that they make is that they can in real time do some like, I didn't know this was even an issue, but I guess if you're in NVIDIA, you know this, like there's a lot of different effects that they would like to be able to do to videos in real time, but they can't because of these issues. And so here they're actually rendering this. This isn't a photo, this is a render. And their point is that they can do this blurring effect in real time, which is that something that I guess beforehand you couldn't. And then over here, I'm not exactly sure what effect they're doing, but this is again another real-time render, which is pretty impressive. I thought these were both photos. Yeah. Okay, I won't go into too many more things. I'll just show this because there's just like a lot of detail that's worth reading if you're interested, but not if you're not. I just like this one because I like zooming in on these to see like what's the thing that the author picked up on that I can't even see. So here they're testing like whether you actually need the MLP or whether you can do a linear mapping. And so this is the reference image or rendering, because I think this is a rendering. This is the MLP, and then this is the linear one. And I guess it's slightly worse because it's more grainy. You can see it worse, that it's worse down here than over here. So anyway, this is an experiment to show that the MLP is useful and helps increase performance. So anyway, lots of cool different images, and basically what it's showing is that we have like a really simple state-of-the-art method for learning neural graphic primitives that can run in real time. So I think we might see this in the future in video games, and it will be one of the methods by which we start having like really good graphics in video games. We'll have to see.
For the metaverse.
Yeah, exactly. That's true. They do mention some things that that they want to work on, which I thought were interesting. Back. Okay. So they have like a discussion in future work. And one of the things they thought would be to learn the hash function would be cool, because now they chose the hash function. And in order to do that, they would have to develop a continuous formulation of indexing that is amenable to analytical differentiation, which would actually be useful in a lot of problems. Or they would say applying evolutionary optimization algorithm that can explore the discrete function space.
How do you develop continuous formulation index?
Well, that's why it's future work.
But isn't it, so they already like, they've already stationed where but the 2 points that are close together, they hash also close together.
Yes.
So it's,
That's kind of be the continuous property.
yeah.
Right. Yeah. There's like a means. So
Yeah, I think so, yeah, but it's I think also more. I don't really do it.
okay.
Then they say they want to get rid of the graininess that you see in those images. That's one of the limitations. For some reason, which I didn't fully understand, their current method doesn't work in the generative setting. So it says our hash encoding adds an additional layer of complexity it's because the mapping isn't bijective, that you can't use it in the generative setting. I think it has to do something like you can't easily do density and density estimation with a hash table in your model.
Is it not budget? Oh,
It's not bijective.
because wow, because there can be conditions.
And then the last thing that they said, which I thought was interesting, was that they would say, like, we hope that parametric encoding such as ours can lead to a meaningful improvement into general attention-based tasks. So, for example, what if you took this method and used it in a transformer? I don't know if the first question is, how much of an impact do position encodings have in a transformer? And if they do have a big impact, maybe this would, but maybe not.
They're lost because they always use them. Last one, the real take those solutions.
But they hardly explain them.
Yeah.
It could be that they started using them and then they had a deadline for the paper where they're like, I'm not going to remove this and redo all my experiments.
So then everyone kept using it.
Yeah,
It's
I don't know, maybe it is useful, but the fact that it's not like an experiment or the method isn't even really explained in the paper. Usually, in my opinion, those are details that aren't as important, considered as important, but I don't know. So yeah, that's the paper. If anyone has any questions, feel free to ask now. No? Okay. And we'll just look at one more cool image and then we'll close it.
You should do more NVIDIA videos.
Why? Because they have good images? Yeah.
This is hard.
Yeah, here's another example where they had an offline rendered cloud from Disney. And then this is the rendered version that was rendered in 32 milliseconds. And then this is some using path tracer to render it. I guess so this would be the analytical way. So they're showing that it's even better than the analytical way.
It's also actually very, you can save a lot of money, right? Because if you render like the whole movie, takes like hours, and then you make machines that will not there, so that was that much cost, that would be really like economical problem.
Yeah, I heard that
Great.
when like the really big production studios make a movie, they actually have people who like almost go through it frame by frame, and it takes months to finish because of that. That's crazy.
Under the limit or because their cost is so much higher.
Mm.
Or, yeah.
gonna stop recording.